Hello everyone, let's look at the second task of this week 66, and the task is power integers. You've got a number n, write a script to check if the given number can be expressed as a power mn, where m and n are positive integers, otherwise print 0. Make sure that both of them are more than 1. Bonus task: if there are more than one ways to express the given number, as this, then print all possible solutions. Yes, so for example, there's number 9, and we can say that this is the second power of 3. If it's 45, it's not possible to express the number in this way, then we are printing 0. And finally, if it's 64, there are more than one way to print it, and just list all the options if we can find them. That's right. So let's see at the Raku solutions. Here is the list of Raku solutions, and I will start with... Let me start from the end this time. So Roger Bell West, Raku number 2. By the way, also it's really interesting to just click on these blog links. Sometimes there are really interesting explanations of how people approach the tasks. But still, let's look at the solution first. Yes, it's quite a big solution, and it is... well, first of all, there are some tests in the beginning. 36, 6 by 2, 9, 45, and maybe there should be an example when there are more than one way to express the number as a power of two integers, but nevertheless. So where is the main program? The main program starts basically here. The only function here. We've got this input number, and so we are trying here to express the number as the product of prime factors. Okay, so we found one of the most difficult ways to approach the task, to solve the task. Well, it's probably the fastest way, but it's not the straightforward of just trying all the possible combinations. Let's see how it does. So how we're doing it here. So factor, we start with 2, and the infinite loop, which will break when we will finish the end, and that's the only exit point. No, there's another one here, right? Yes. So while the number first, this is the copy of the initial number. Actually, we could use is copy here, just to not create a separate variable for that, because I believe we don't use this one anymore, right? Right, it's only once. It's used only once, so we can just add the is copy trait here. Then we are trying to find the factors, and how we do that, we start with 2, and while this while the number is divisible by the current factor, which means that the remainder of the modulo operator is 0, we can make the number smaller. So we divide it by this factor, we increment the counter, and repeat while we find a factor which is not the factor of this number, right? I would like to add a comment about this thing. So this thing is a really thing that we can express differently in Raku. Let me explain what I mean. So for example, I have two numbers. My number A is 10, 20, let it be 20. My number B is 5. So definitely I can divide 20 by 5 without any remainder, and I can check if we don't need parentheses. If A modular B, right, we can print this. It will be definitely, it should be 0, but, well, yeah, let's first mod Raku. Let's first run this program with this value. So let's run this program, Raku mod 2. It's a 0, but the thing is that there's another operator with double, which is true, double %. And if, for example, I want to make sure if the first number is divisible by the second number, I can always use something like this, right? Or I can yeah, so there are a few ways. The first way is this one. It's the traditional way. In C, maybe you would say it like this, but actually in Raku, it's simpler to do it like this. A is dividable, so this is the dividability operator. Am I correct? So let's look at the documentation. Docs Raku %%. What's the correct divisibility operator? It returns true if basically this. So you see, so we don't need to type a lot of characters when we only can type a few characters. Well, actually we only need to press the second %. Say okay, or like, you know, in single quotes, if this is correct. So right, okay. If it's like 21, then it's not okay, so it's not possible to divide 25 by 5. So that's the solution. So this and this and even this together with the exclamation negation is exactly the same. So it's better to use just the check with the divisibility operator. Right, let's go back to the solution. So we found some factors, and if the number is less than 2, it means basically that the number is 1, because after any division we can only get 1 but never 0, right? We finish last, and where is this? And here, right? And then we will make some additional change test. If it is 2, yeah, well, actually, yeah, it's if and last, and then if. Basically, this is an else if to this, right? And what does this mean? So if we found at least 1, then we pf prime factors. So we just add the prime factor to our storage hash pf. So if factor is 2, then we increment the factor. Okay, and we repeat this. We increment it by 2 until this. So we are trying to find if it's a prime factor or so yeah, so this is the end of the loop. So in the loop, before the loop, we start with the first prime number 2, and then after one cycle of this loop, we need to have the second, the following prime number. And here, what we do is just trying to find the number by looking at the next numbers. Well, next every second next number. And as soon as we found this prime factor, we can continue the loop and continue this. After we are done, when we entered this branch and exited the loop, there's last check if maximum value of the found prime factors is the same as the minimum. Interesting. So if the maximum is the minimum, what does that mean? Does that mean that there's only 1 or not? If the maximum prime factor is the minimum prime factor, if not, then return 0. So basically 0, this is the case, right? And if max prime factors, I wonder how does that work. So maybe I want to make it like this. Let's play with this a bit. So for example, I want this single factor of 9, right? And I want just to print this storage here. What will it give us? Raku prime, right? So it's, yeah, basically there's only 1. So if the maximum value, I wonder if we will have, for example, 64. So the only prime factor is So let's look here. So here is so this is the prime factor, and this is the number of its repetition. So like 64 is 2 powered by 6, right? Right. And what was the example in the task? Where is it? 66. 64, it's also 8 and 2. So we found basically the only one solution with the lowest first number. That's correct according to the definition, but it doesn't give us other solutions. Yes. Okay, so but I'm interested in the situation when there's only like 45. Right, so there are 2, 3 squared plus 5. 3 squared is 9 plus 5 multiplied by 5. So it's 9 multiplied by 5, that's 45. I mean, this is correct. So yeah, I wonder if we can replace this line with something like my indentation is different. Something like, again, these parentheses are not really required here. If basically the number of keys is 1, right? Is it the same? It looks like yes. And why did yeah, because we don't print this. So it's 0, and if it was 9, then it's 3 powered 2. So I believe this can be simplified. Okay, let's go next. That was a solution, and let me repeat that this is a solution, a pure mathematical solution, a really good approach that we think first, and we just do not try to just test all the numbers that we can. Let's go to Muhammad and var and solution number 2, and here is the main function as usual, and again printf can be replaced with just some string interpolation, including the function. Yeah, maybe the function's a bit. So basically, I will tell you what I mean. I mean that instead of this, I would say better something like this: n equals either this and get this function here, or maybe just this, right? I find this solution a bit like Raku, more in the spirit of Perl and Raku. Okay, never mind. The main function calls the getPowerIntegers function, for which accept integers, positive integers, and so we are trying to collect. I wonder why we are using a scalar here, because this is just an array to which we are going to push some elements. So basically, I would say like add power integers and an empty array in the beginning, but then we start with 2, and again with 2 we go up until this square root of n, because otherwise there's no way to go any up, and just multiply, just make the powers of all the possible combinations with these numbers, right? And if it is the number, then we push. So this solution will collect all the possible variants. Let's run this. cd Mohammed Raku solution number 2. So yes, and 45 is n is 45, so 45 is 0, and well, 45 is not 0. And if it's like 81, yeah, so there are 2 possible solutions, and for 62 there should be 3, right? Yes. Yeah, right. Nice. Good. Going next. Next is Loren Rosenfield, and his solution is here. We start with the main function. Again, see, so there's is copy, which is really useful in many cases when you want to change the value, and I wonder if we really change the value here. It looks like not, at least not here. Maybe the find powers function changed. No, it doesn't change either. So it's positive integers. So say 0 if there are no elements in this power, and otherwise just list all of them. So we have to look at find powers, prime factors. Again, so there's a separate function to find prime factors of the number. Here I'm going to, wow, so it's interesting that there's again this pattern. So we are using it only once. Well, yeah, and here for so yeah, so basically this one is the copy of original one. So basically I think we don't have to have this copy. Prime factors. So for prime, what is wait, so yeah, we call these prime factors. Okay. For all the primes, primes, what is primes? There's a pre-computed, well, it's not actually pre-computed, it's lazily pre-computed, so it's not computed until it's used. List containing array containing the prime numbers, well, potentially until infinity, and then we just go through them and compute them on demand. And this div is basically a prime number from this row. And while divisibility operator is here, while we can divide, basically this is a really good thing, because when you think of how this program works, you can just tell while this is divisible by that number, so you don't have to express your ideas while this has no remainder after it's divided by the number. So just this divisibility operator is really good thing by itself. And we collect the prime factors. This is the integer division, if I remember correctly, right? Or is it not? Or is it just with different precedents? Integer division, right? So it rounds down if the result is not integer. But as soon as this is an integer, yeah, really. So we will divide it by any number. I'm a bit like worrying about this line. And finally, if number is, so if we reached 1, so if we divided by these primes, and in the end we found that it's 1, then we can return the collected data. If not, then we add the number itself, the number that was left, I mean, if it was not the original number, and then we return the prime factors. I believe this is a correct solution. So we found all the prime factors. The only thing is, does this contain the prime factors, like if there are more than one, how many? So let's just look at how it works. So you see, so today's task is more about mathematics than just pure programming. Prime to Raku. Hey, please save me. Wow, that's a bug. That's, hey, you don't want to save it. Oh, what? Right. So editors are not ideal. TXT. Oh. Yes. So let's say, for example, prime factors of 9. It should be like 3 and 3, right? And I wonder how many 3s I will see in the output. Raku prime 2. Both 3s are there. That's what I wanted to know. Right, let's go back to the solution. So we found all those prime factors, and yes, so we do not go any further than the square root. By the way, this is not an integer, right? So we have to keep it in mind if it's appearing in some loops or sequences or somewhere else. If there were no prime factors found, it means that the number cannot be expressed as the power. Then among these, out of these prime factors, we make all the combinations, all the possible combinations, and map them. And okay, so finally we take some unique things. So for example, if we will take this solution, so it gave us 3 and 3. Let's think, so we get 3 and 3 here. The combinations are, what are they? Maybe can we make this as a continuation? So it's prime factors, right? And this is prime factors combinations. What is this? Like this, C, right? So here are these combinations, whatever it is. Then we map them. Let's stop here. So then we map them by using this block, which has the reduction operator for multiplication. So basically, which multiplies all the elements in the current loop, on the current. Yes, so it's 3, 3, and 9. No idea why this one is here. And then we grab everything that is less than maximum and is bigger than 1, right? A maximum is not declared, that's right. And what was the maximum here? The maximum is square root of n. So basically, for example, for this example, we have 3, and we will filter out everything which is not 1. So we got 3 and 3, and then you've got this unique method call, and 1, 3 is left. And this is in the factors array, which then what are we going to do next? So we have the factors. Now we have to find the powers, I believe, right? Because it's pushing here. So we are looping over factors. The factor is div, something like the same loop as here. And for every second number, no, I'm wrong. It's not every second number. For every number from 2, which is the test power, we stop if we go already outside of the number. So if this combination of the two numbers div and x is gives us too big number. Otherwise, we just collect this if we didn't exceed the limit, and if we found a number which gives the result. And finally, so yeah, this loop will collect all the possible combinations. And finally, we will just print it here. Let's run this program for how does it. So it accepts, where is the main? So it accepts the number from a command line. Loren Raku 2. So let's give it 9, 3 and 2. Let's give it 81. There are 2 options, 64, and finally 45, right? There should be 0 here, right? 0 comes from here. All right, so this solution works, and it's an interesting solution. So it's using combinations of finding prime factors and then just testing all the combinations which can give the result. Javier, solution. Tests. We just test a few numbers. The 3 different possibilities was this, where there is like nothing found, 1 result, or more than 1 result found. function power, what does it do? So it I just scans the whole basically square of the n by n size, well, without this first element with the value of 1. And if it's big, just as we saw in the previous program, we just stop this. Otherwise, if we found the result, then we just take it. And again, if there was something found, we just list them comma separated. If not, print 0. Raku 2. Yeah, so power 16, it was like, yeah, so this function returns us a string which already contains all those commas and stuff, so we'll just test if the string is correct. Right, going next is Jaldar number 2. We take the number from the command line. Is power, but I believe it's not like is, it's not boolean. It just gives us some list of results, and if it has something, then yeah, again, so see, so there are like 3 programs, and in all of them it was a bit differently how people join the results. So here the curly braces are used, and otherwise it's 0. So is power, which is actually like find all powers, I believe. I don't know how many, probably everything, because I don't see that we break the loop after we found the number. So if the number was 1, then push. That's I don't understand this one. I mean, why is it show so difficult? So my result, right? 1 join, so we can just I mean, do it like this, right? What's the difference? Raku, so this file I will not keep for Raku R. Results. Yeah, so it basically just a string, so I don't understand why we need to compute this if it's only a constant. Okay, then if the number is bigger than 1, then again from 2 up to the square root of this, so the number, the test number is m, and yeah, we just try to find all the powers with these integer numbers. So while it's less than original number and p is positive, what is p? P is the so it's not positive, it's basically if p is not 0, right? Because it cannot be a negative number. If p is number, then we collect this number again by joining. Yeah, but again here I believe instead of this we can just write something like this, right? So even this. So what's the purpose of a separate join and an array? Then we increment the number and we compute the next value. Yeah, in such loops it's always like you calculate the result before the loop and inside the loop twice. Well, it's every number is every value is calculated twice, but you have 2 lines of code which do the same. It's always a pain to get rid of such thing, but nevertheless, so it looks like it works. Let's run this solution. Dar Raku to number 9, right, number 45 and number 81. Right, so there are 2 solutions here found, which is good, so it works. Next, what is next? Next is Colin Crane. Colin Crane solved this like this, and I see that there are factors. So again, we are finding some prime factors, and he uses a quite big already number. I wonder what does it give us. 324. So there's only one solution. So first we decompose the input number, decomposes the function here, and so it will, I believe, given a number, returns an array list of prime decomposition factors of the number. Then we do something. Let's look at the decompose function. Decompose function, so it's this prime list, so it's similar to what we saw with Loren's solution. From 2 to square number, well, yeah, just because square is not always an integer, we just round it down, basically, by taking its integer part and grabbing all the prime numbers. So yeah, it's also compare like this, right? And what we saw here, like this. So the order of so you see, so you can call a grep as a method, or just use a grep as you used to use in Perl. Both are correct, but probably everyone can choose a different variant, and probably like tomorrow I will use a different one than I used yesterday. Okay, so we've got prime list, and unlike, again, so if the second difference here is that yeah, I removed it, so it's not a lazy infinite list, it's just the defined list with very well-known edges. Then we take the first one by shifting it from the date list, and while the number is less the original number, by the way, again, this is a copy, because yeah, finally the copy is used properly, because we just modifying the only variable, we do not introduce any other variables here. So we divide it by the prime factor, and while it is divisible, yeah, so again, so basically the program does indirectly two divisions, right? First it tries to divide number and tells us if it is possible, and then we make really a real computation, which we'll just use. Yeah, probably it can be a bit more effectively implemented, but nevertheless, so if it is possible to divide number by this given prime factor, we just keep it. So it will give us the list of prime factors, right? And this, like if, for example, number was 9, we'll only get a single number in the result, I believe, like not 3 prime 3 Raku. Say decompose 9. Oh, no, I was wrong. But why? Last prime shift. I wonder why we've got 3 2 times here. Because in the prime list we have these 3 only once, and while yeah, of course, yeah, right. So there's no question anymore, because we are dividing the number by this prime factor in a loop until we while we can do that. That's right. So that's my assumption was a bit wrong. So we found all the prime factors, as many of them as we can find in the given number, and then we try to, using these decomposed result, we trying to find the factors, right? The powers, to find the numbers which give us the correct powers, get powers. So we've got this with this function get powers. So let's see what it does. So it gets this prime factors. The only thing that we didn't mention yet, so this function returns you a list, right? So here the array is returned, and this is the hash, and this list is converted to hash using this map method call, and what it does, so basically it will convert, like for example, for 9 we've got 3 and 3 here, and after this transformation we will get like 3 is the key, and 2, so the number of repetition of this 3 as the value, right? So it will just increment. Initially it's absent, so it will be like 0 plus 1, and then so yeah right. So it should be like the hash of all the prime factors and the number of their repetitions. So we take these factors and you also sort them. Interesting. So you either sort them by, so A and B are the so-called placeholders, so it's basically the first and the second. You can call it X and Z or I and J, whatever you want, or alpha and beta. These are the first and second values that the sort function provides us with during this sort process. But the sorting function is either like sorted these or sorted those. So yeah, I don't quite understand why. But okay, so we sort these numbers somehow, either from lower to, yeah, interesting. Then if nothing is there, if factor elements, actually I believe we can just return 0 here before we do any sorting, right? Single factors for prime numbers aren't recorded, but we don't care. Then single factors for prime numbers are not recorded. So it's like 11 number can be, right? It should be 11 here, but I'm not sure. Then okay, so then we take the first power, and if so, probably this is why we need to sort them, because that was the hash. And actually in this array we were collecting the numbers in already sorted, right? Because the prime, what are we going with, the prime value is the next from this list, and this list is already sorted. So basically when we converted this list to a hash, we broke the sorting, and now we want to sort it again, but a bit differently. Okay, so and finally we return the two things, the power, this power, which is the first. I don't understand why that's difficult and what actually is doing. And the base factors are so some mapping of those factors, the sorted one, and the mapping is, so if it is a power, right? If it's the result, wow. So then like something, but I'm interested in this second branch. So if this is false, then we just return instead of, so can we do that? Well, obviously we can if the program works, but I would say it's like from different worlds. This is the result of some computing some expression, and this is just the instruction to return from the function without any values, like this. Yeah, I wouldn't do it like this, but okay. So let's run this program. So go into Colin Crane Raku solution, Colin Raku number 2. Yes, and for example, if it was 45, it's 0, and if it's 9, right? And finally, if it is something that gives us more than one possibilities, then it was a bonus task, but nevertheless, so yeah, it finds the correct solution, right? I don't understand actually what happens here and here, but it works, right? Going next, the solution from Athanasius, and here we go. So we've got some integer in the output, and there's some boolean flag done, and if the integer is positive 1, actually, yeah, we can just add the where clause here to get rid of this check. So we collect the powers into a string, the array of strings, and then just print them joined. If there are some elements, actually, when you check the length of the array, you can just check if powers, that's it, so that's enough. But this is an explicit call of elements, which is also a valid way to check the emptiness of the array. So we just print them separated by 2 spaces, and otherwise we just put 0. And the main function, so again, so the usage function, which we saw in other weeks, the usage check other videos, and the main function, so it gives us some array of strings. So we've got an integer in the input side, and we return an array of strings. So the powers, we will collect the results here. The minimum exponent is 2, since n is more than 1. The maximum exponent is that for which the base m is minimum, also 2. So we've got the maximum logarithm of logarithm. So here is the explanation why we need this max and how we can. So yeah, it's basically a different way, I believe, instead of square root, right? Then yeah, so for this found limit, upper limit, we make a loop from 2 to this number. And so what happens here? So first of all, I see that there's like plus 0.5 and then dot floor. So basically there's the dot round method, which will make the correct rounding of the number. So it's a bit well, it's not needed in Raku because there's round function. So there's a number which is y divided 1 divided by n. y divided, so it's in the power, so it's, yeah, I don't, so it's based, it's maximum logarithm, yeah. So from the recognition infix is right hand side is not negative integer and left hand side is an arbitrary precision integer, then the calculation is carried out without loss of precision. Yes, and so, and then we push this string. Remember that the result is an array of strings. We push this string if the power m powered n is n. And what is m? So basically here we just make the opposite operation. So we've got the number and we just immediately try to find the power which will give us this number in the end if we will put it here. Nice. Yeah, so basically nice. So instead of just trying all the options, we can just make some solution almost immediately, and then we will loop so that we can find all the solutions. Interesting. Wow, that's nice. I really like this, and I want to run this program. So the number 9 is yes, the number 45 0, 64 3 options, and 81 2 options. Right, really nice. And yeah, and this one seems to be really good, well, except this. So yeah, you directly get the number. Okay, Arne, Raku 2. There are 2 versions of the main function. That's why it's multi-function. And so this is, wow, I've never seen this before. Like you can get, yeah, well, basically why not? But you have to invent this approach. So this main function is triggered when the input number is already a prime number, right? What does this one do? And we will see it. Yeah, so this one is a flag indicating if we want to have more than one result. So if the input number is a prime number like 11, we immediately can print 0. So Why waste time on finding the result if we know already that if it's prime? Interesting. And the second one is for all the positive numbers. Then what we do, we just do base. What is base? So base and x, we just make this calculation, and as soon as we reached the limit, we stop, and if we found the power, then we print it immediately, count the number of attempts, and exit if done. Wow, so that's also an interesting pattern that I kind of didn't use myself. So we have this construct in parentheses with a few instructions in it, and the postfix if. So instead of using the code block in curly braces after the if test, what it's seen here is just the postfix if with some list of statements. And finally, if nothing is found, so if this match was never increased, we press 0. So yeah, here the most interesting part I find is this one, and syntactically the most interesting part for me is this one. Raku, Arne, Raku. So the first number is 9, the second number is 45, like 11, which is the prime number, right? And 64, and if you say 1, then it's only the first result, 81, for example, right? Yeah, so yeah, it works perfectly. How many solutions are there? There's 1, 2, 3, 4, 5 solution. Okay, going next. Next here we've got the solution with the main function is copy again, and for so see here's the different approach to find the maximum number is just divided by 2, which is kind of also okay because for small numbers there's no big difference, and result, while result, one this different indentation, while this result is more than 1, then we try to divide the number as many times as possible. We count the times, and if in the end we've got the 1 in the remainder, then we just collect the number, and again we're collecting the string already. So if there's something in this array, we print it, otherwise it's 0. Let's quickly run this. Ulriki, Raku 2, so 9, 16, let's do it 16, yes, right, and 11, 0, right, so it works, nice. And 3 more solutions, right, or 4 or 5 or 6, oh my god. So this solution from Shahid, long list, so what is, so I have to copy this to see how it works. There's no n, so I have to make the program. Let's make it. Let's make the program so it's like this, like this. My n is 9, and then print. So I don't understand yet what it does, what the program is doing. So Shahid Raku, right? But it's like, okay, let's just run it. Wow, nice. So it gives us, now I understand it. Now I kind of understand it. So what's like, for example, 16. It's 4, 2. Wow, that's cool. That's really cool. So what these numbers are is basically the code points of those superscript numbers, and using this shift, what's the correct name of this operator, which will basically apply this method call character to each of these numbers. And also it's interesting how the list is constructed. So there's first of all a range. Well, the second part is a range, and then we flatten this, and there's some randomly located code points. So let's maybe just call this one from the command line. From the command line, what do we have to do? There's definitely something wrong here. The wrong thing is enable call person with the type object. Which type object? So for example, my code points is this, right? Then for each code point I call this method. Yeah, so and so basically I can just do it like this, right? So yeah, here's the result, and this dollar is actually this dollar coming from the map method. Nice. So but I wonder, why do we need to use these codes? Why we cannot just make this like something like that? I mean, definitely we cannot believe. Okay, then, so this is what is the value and what is the key? Ooh. So okay, let's start from the, I even don't know from where, probably from here, right? So 4 so so these keys, key and value methods are called on something that this 4 is preparing for us. And what does it do? So again, for square root, we map this so that it like the key is the number and the value is the logarithm of the original number on the base of, with the base of one of these numbers, right? What does this log is doing? What is the argument of this? Oh, actually the second argument. So yeah, there are, so there's there are two, the number itself and the base, right? So the base is like from 2 to this square root of n, and then from these numbers it's already a map, and then we grab in the map. And when you grab the map, you have this again value and key methods available for grabbing, and we are grabbing the map so that the value is the rounded down value. So basically it's it means that it's an integer, right? So we can make some other check if it's an integer. By the way, I wonder how can we make the check if the given number, the floating point number, is an integer. So this is the option. Okay, so then we will have this value here, which was grabbed here, and the key, basically I believe this is, the key is this one, which is one of these numbers, right? And then we print the key, and this construct gives us, so it splits. For example, if the power contains 2 characters, like 3 powered by 12, then for each of those numbers of those digits in the value of power, we will convert them to this superscript. So for example, let's find an example of how to run this program for the number which is like this, for example. So the power 2 powered by 10. So I expect to see 2, something is wrong. What is wrong here? Did I break something, or it doesn't work? Yes, I broke. What did I break, I wonder? Right. What? So you cannot do it like this? Really? Missing block apparently claimed by an expression. Wow, that's strange. So it works if it's a clear postfix in the same line, but it doesn't work if I add new line, right? But I can always do it like this, I believe. All right. So let's have this power, tens power, where there are 2 digits in the power, and this is the second digit. Yeah, the output. Wait, is it a space? It looks like a space. Why there's a space here? So, for example, if I will just do it like this, I will have these 10, right? But if I will map this, I will split this using a comb and then map them into digits. So it's 8, 9, 10, 11, 12, 13. It's 6, 7, 8, 9, 10. So 10 digits. So I wonder where does this space come from? But yeah, that's the thing for homework. But nevertheless, so we see, so it's possible to use superscripts in the output as well, and that's one of the ways of getting them. Let's go next. The next solution is from Node, and here it is. Are there any explanations? No, that's just the copy of the description. And so we test it on 5, 45, and 64, right? And what is here? Here is, yeah, that's the direct search in the big list. The only thing I'm like immediately looking at is this power 1 half, which is basically the square root. So from 2 until all the square root of this, and another array like this. We will create the possible list of possible powers, and then we'll just grab the thing which gives us n in the end. The only thing, why is it EQ operated? It's because it's comparing strings, but we are getting the integer, so probably equals is a better choice here, I believe, right? Because what is this is an integer, right? Right. Let's maybe just make a quick investigation. And what does this do if the number is, for example, okay, first number is 9, so it's 3, 2, and 3, and I see there's immediately floating point numbers come into our consideration. And what happens if the number is, for example, like 10? Okay, let's make it 100. 100 is not a good choice. 99, for example. So from 2, yeah, I wonder what this one gives us. Why? So from all the possible combinations, but right, so say for this one, right, so it even that the right edge is not integer, we still get only integer numbers here, right? Okay, no, that's fine. That's yeah, I didn't think about this. Nice. And instead of square root, we're just using the power 1 of 0.5. Right. So we collect all the possible combinations and of the number in its power, and if there's something, we just print it in this form, yeah, without any superscripts, but nevertheless, otherwise we print 0. So let's go to the solution, cd node Raku 2. Right, so all the examples that we want to see are here, all the 3 cases. Right, next there's no solution here. From Mark Anderson, the solution is like this. So there's the positive integer in the input, and then we gather and take the numbers. I really like using gather and take, even if there's only one take inside the gather block. So it will gives us an array for which we just print the values, or that's interesting. That's an interesting constructor. So if this array is empty, we replace it with 0 basically, and the 4 gets 0 and it prints 0, right? Nice, really interesting. So what's there inside? So inside we go going up until this square root, and yeah, again logarithms, the log floor. Yeah, so if log floor, oh my god, log red denominator is 1. So we are trying, so we are taking the number and the power. Again, we saw like a few solutions back that there's the direct calculation of the potential power, and if the red denominator is 1, so basically it means that actually this is an integer, right? So there's another solution of how can quickly check if the number is just convert it to a rational number and check if there's 1 on the below the line. Right, interesting. I wanted to run this solution too. So for 9, for 16, and for 11. Yeah, all those cases work really good. Actually, really well. Look at Raku number 2. Here is the solution. So the main function takes the number, and we are trying to find within all those numbers, except the last one, except is indicated by this hat, is power, watt, and base. Wow. So is power takes some named parameters for some reason. Yeah, but why not actually? Yeah. With some default values. So this is the way to pass named parameters in Raku to a function, and then so n can be expressed as the power of some number, dot say, and found is true if we found power. So again there's some construct, but this time it's connected with the double ampersand, and if it's true, then it's found here. So, and if so if it's not found, or unless found, we print say. Right, so the most interesting thing, well, the thing that makes the main work is power function, and it returns 0 if the input number is 1 or the same as the base, so the power is 1. Not a power if not. So yeah, so we started this video with an example that basically we can reduce this to so put 1% here and remove this one, right, and all those parentheses also. If here should compute the power. So yeah, so finally we reached the actual job. Power increment, it's either plus or minus 1 depending on the two different cases if this number is bigger than this one, but I believe there should not be such cases in but okay, nevertheless, I wonder what which additional examples it can find comparing to our previous solutions. So nevertheless, so we will just what's the purpose of this? 1 multiplied by power increment. It's always power increment, right? Multiplying by 1 gives nothing. Result is the power, and while it is, we just make the step to increment the power and continue until we make it the result too big, and if the number is the desired value, we return power, otherwise we return nil. Run it, Luca, Raku, 2 with number of 9, for example. I wonder why. Yeah, so it's named argument. Why to use named arguments if there's only one parameter here? 9 can be expressed as 3 power 2, right? And for example, 11 it's 0 and 64. Right, so there are 3 options, I believe, as well as 81. Yeah. What if like we do it like what is it, like 16? I don't know. It's an integer, right? So yeah, you cannot do it. Right. Okay. Good. Good. The next solution, yes, it's mine, and here is the solution by me. Here it is. Yeah, maybe I have to explain some details of it. So this one is definitely the same range as we saw earlier in a few other solutions. And again, this square root can be a floating point number, not necessarily an integer, but it's not important. So we repeat it twice. So it will give us something like this. And then we make this, we compute the powers of all those combinations. And finally, we check if this input value n is in or is an element of this list. So simple. So let me just run this, and I didn't copy this. Let me run it just to see that it Raku ash. So it prints true. Yeah. Yeah. So yeah. Basically, the solution is short, but actually it doesn't give us any results. So it's just it just gives us the indication of the possibility for this number to be presented as the power of 2 integers. But nevertheless, so yeah, we can update this. But what I wanted to say is just in this solution, I want to show the use of reduction operator and the set operator, which can be spelled out as elms, if I'm correct. Elem. So it's it means that n is an element of, but in better and Unicode notation, it's like this. Okay, that's it from the second solution of week 66. It was a really long review because there were lots of mathematical things that we wanted to, that I wanted to take a look at. I hope it was interesting. Don't forget there's the first solution of this week, task 1 of week 66, and there are other weeks as well, so take care.